I assume. Fine. So we did this mapping circus for two of the transfer functions, and now we're in a position to state the Nyquist formula. So let us see what is that Nyquist criterion. So Nyquist criterion is much simpler than what mapping we did. So it is expressed mathematically as just equation z equal to p plus n over. Nyquist criterion is over. So what is this z and p and n? So n is net encirclements around the point minus 1 plus j0 in GH plane. So as I said earlier, we are forgetting the intermediate step. We are dealing with only GH plane and S plane. So n represents net encirclements around the point minus 1 plus j0 in the GH plane. So the encirclement may be clockwise or anti-clockwise. Therefore, for clockwise, n is positive, and for anti-clockwise, n is negative. So only 29 students are present. So I assume they don't have a sufficient data. So they can watch the videos later. So meanwhile, P is number of poles of G of S H of S or 1 plus GH on the right half of S plane. Please listen carefully. It is number of poles on the right half of S plane. And Z is equal to number of zeros of 1 plus GH. So number of zeros of 1 plus GH. So zeros of 1 plus GH represent the characteristic roots of the closed loop transfer function. We had seen that during the beginning of the class. The number of zeros of 1 plus GH or the roots of characteristic equation on the right half of S plane. On the right half of S plane. Fine. So n is net encirclements, p is number of poles of G of S H of S on the S plane. So this both n and p are available in these diagrams. Okay. So n represents this encirclement. So since there is a clockwise encirclement, I can find n. P is number of poles of G of S H of S or 1 plus G of H on the right half of S plane. So for the given transfer function, there is no right half pole at all. Okay. But Z I need to find using this formula. And whatever the value you get, that value represents number of zeros of 1 plus GH or the roots of characteristic equation that lies on the right half of S plane. So what does that mean ultimately? What should be the condition for stability? Should we have any characteristic root lying in the right half for stability? No. Therefore, for closed loop stability, Z should be equal to 0. Anybody not understood these terminologies? Should I explain again? Anybody not understood these terminologies?
Sir, can you explain once again?
Yes. So this mapping and all we did. Why? Because Nyquist has given one formula and we need to substitute the values in that formula to check the closed loop stability. So as I said in the during the beginning of the class, given an open loop transfer function, you should check the stability of closed loop system using Nyquist criterion. That is our task. Okay, given an open loop transfer function, you should check the stability of closed loop system. Fine. So that is our task. So to check the closed loop system stability, one can easily say that there shouldn't be any right half pole in the closed loop transfer function. Is it finally Lohit? Who is that? Who asked me the doubt?
Yes, sir.
There shouldn't be any right half pole for system to be stable. So what Nyquist have told us, you find the number of right half open loop pole. Right half open loop pole. You get the information of only open loop system. And you check the number of encirclements on GH plane. And when you calculate Z, the Z will give you how many number of roots of the characteristic equation of the closed loop system on the right half. So if there isn't lying any right half pole for a closed loop system, you will obviously end up with Z equal to 0. Therefore, system will remain stable. So let us apply for our system and check it out. I will come back to you again. Okay. So let us see. For this particular example, there is one clockwise encirclement around -1. Everyone agree with that? Okay. And what is P? Is there any pole of G of S, H of S lying in the right half? No pole is lying in the right half. So P is 0. So what is Z equal to? Z equal to P plus N. You are getting Z equal to 1. So therefore system is unstable. I will conclude that system is unstable. As to be specifically, closed loop system is unstable. So let us check here. The same example I am taking. S minus 2 divided by S plus 1 into S plus 1. Open loop stable, but closed loop you are ending with unstable. So you got Z equal to 1 because one of the pole is lying in the right half. Okay. So the one who asked me doubt, can you tell me the roots of this characteristic equation using your calculator or anyone else? For this particular example, what are the closed loop characteristic roots? I'll wait for your answer.
0.3 and minus 3.3.
0.3 and minus?
Minus 3.3.
Yeah. So one of the root is lying in the right half, right?
Yes, sir.
So our closed loop system is unstable. So the same information Nyquist is giving in his own way of mapping technique. Okay, in his own way of mapping technique, this mapping has a very huge advantage when we design controllers. So we'll come to that part later. Meanwhile, let us check for another example. So for this example, the one who asked me doubts, can you come back please? Shrikar or someone? Yeah.
Sir.
Shrikar, now look at this example.
Yes, sir.
So S plus 2 divided by S plus 1 into S minus 1.
Yes, sir.
This is open loop transfer function. Open loop, is it stable or unstable?
Unstable, sir.
Open loop is unstable. And closed loop, what we had got? In the table, closed loop was stable. I mean, closed loop transfer function was stable.
Yes, sir.
Okay. So open loop unstable, closed loop stable. Let us verify it from the point of Nyquist criterion. So Nyquist criterion is straight away Z equal to P plus N. How many poles are lying in the right half? How many poles of GH are lying in the right half? 1.
1.
So P is 1. Correct?
Yes, sir.
Next, find N, number of encirclements around -1. How many encirclements are taking place around -1? There
1.
is. And is it clockwise or anti-clockwise?
Anti-clockwise.
So what should be N?
-1.
-1. So substitute Z equal to P plus N now. What you will get?
0.
0. So it means in the closed loop characteristic equation, there is no pole in the right half, according to Nyquist. Understood, Ashikar?
Yes, sir.
So 1 minus 1 is 0, which means closed loop system is stable. We had got the same answer without doing Nyquist also. Okay. So I had to tell these things because, as I said earlier, it is challenging from the perspective of teaching also. I had to convince you that without doing Nyquist, what answer we got, with by doing Nyquist also we got the same thing. That I have to convince everyone. Fine. Then we did for the few examples, first and second. Now we'll do for the third one. So the third example is s minus 2 divided by s plus 1 and s minus 1. So both case it is unstable. Open loop and closed loop both are unstable. So let us do it quickly. The question is check the closed loop stability of the given OLTF using Nyquist criterion. That is g of s h of s equal to s minus 2 divided by s plus 1 s minus 1. So I will take only the s plane, mark poles and zeros. Now there is one pole and one zero in the right half. So let me decide a closed loop contour, appropriate closed loop contour. Let me list out all the points of the closed loop contour. Now I am skipping 1 plus gh. I don't need that. I can make use of the previous conclusions. I'm skipping 1 plus gh and directly coming to gh. And I will mark minus 1 because it is important for me. So if you start mapping all the points directly on the GH plane, this is what we get. Okay, the set of points. So first starting point is plus 2 on the real axis, second point is 1 minus 0.5, third point is in the first quadrant, fourth point is also in the first quadrant. Okay, this point is also in the first quadrant. Something like this. We get some shape like this. Okay. And the complex conjugate contour is symmetric to real axis. Okay. So these are all complex conjugate. So now, is there any encirclement around minus 1, Srikar?
No, sir.
Not at all. So n is without any doubt 0. Is there any pole lying in the right half?
One is done.
Yes. There is one pole of GH lying in the right half. So P is how much? 1.
1.
Now directly calculate Z. Z equal to P plus N, which is equal to 0 plus 1, equal to 1. So Nyquist gives us information that there exists a right half pole in a closed loop transfer function. So therefore closed loop system is unstable. Okay. So this particular example, open loop is also unstable, closed loop is also unstable, and there is one closed loop pole which lies in the right half. So now if you come back and check out this table, sorry, if you come back and check out this particular example, if you calculate the roots for this, you definitely get only one root lying in the right half. Okay, one characteristic root to be specific will lie in the right half. That's why the whole closed loop system is unstable. Fine. Shikhar, is it fine for you?
Yes, sir.
Yes. Anybody else has any doubts? I'll wait for 2-3 minutes. So the final conclusion is map S plane to GH plane. Then check whether there is any enclosement or encirclement around minus 1 on GH plane. Then accordingly find number of P. Then substitute in Z equal to P plus N. So this is one hint I am giving you. Without calculating the Nyquist plot, you can still get the closed loop stability. So in the exam, if you get a question about Nyquist plot, first confirm if the closed loop system is stable or unstable. Then accordingly proceed. You will get the correct answer. This is cross verification also. Okay. So now you may have many questions like what if there are more number of poles and zeros in the given OLTF? And what if the poles and zeros are located far away in the right half of S plane? Okay, right half of S plane. So for that, let us make the closed contour, okay, the closed contour of the S plane bigger. Okay, instead of this small contour, I will take a big contour. I will take a big contour. So how big is the question? So for me, the entire right half of S plane is the solution. Okay, I will take the entire right half of S plane. Okay, because I want to check the encirclement, and if one of the pole is say minus 100, sorry, lying in the plus 100, then this contour is not sufficient for me. So I will take the entire right half of S plane. Or the Nyquist suggested that to accommodate all the right half poles and zeros, whatever is their magnitude, it's best suited to consider the entire right half of S plane. So now you can ask me another question. Why can't we consider the entire left half of S plane for mapping? Why only the right half of S plane? So that doubt should be answered by Nyquist only. He had something in mind and he ended up in giving some good conclusion out of it. So for that he considered the entire right half of S plane. So it's not that it is not possible to map it, the left half of S plane to GH plane, it is possible to map, but you will end up with no conclusion. Okay. So those conclusion points are still far away. Before that, as of now, you understand what is about Nyquist plot. Nyquist plot is it is the mapping of right half of S plane onto the GH plane to check encirclements around -1. So that's what Nyquist have done. Fine. So if I would have told this sentence during the beginning of the class, then it was very difficult to follow. Let me show you the entire right half of S plane, how it looks like and how you can locate the points. So we have points in the positive axis up to infinity, points on the real axis up to infinity, and points on the negative imaginary axis also up to minus infinity. So the entire right half of S plane can be imagined something like this, all points tending to infinity. Okay. So this is first point, second point, third point, fourth point. So in the first point, it is origin. Second point is where I will say omega tends to infinity, not equals to infinity. Omega tends to infinity. And fourth point, I will tell omega tends to minus infinity. Then this circle, for the circle on the right half side, I will tell the entire right half of S plane is something where r tends to infinity. Okay, where radius r tends to infinity. I can define it like that. And this vector of radius will rotate from or with an angle of 90 degree to 0 degree to minus 90 degree. So this vector rotates from here to here, then it covers the entire right half of S plane. So these 4 points cover the entire right half of S plane. So I have to map all these points on the GH plane. On the GH plane. It's very complex. I mean, this is complicated method. Is it complicated method? Yes, of course, because so many points now, infinite points. So for that, we use a shortcut. So I'll name the points as A, B, C, D so that we can write these points conveniently. So ABCD, I will divide this ABCD contour as different paths. Path AB, where omega equal to 0 to omega tending to infinity. Path AB, then path BCD is a semicircle where the points I can define as r equal to e raised to j theta. Okay, so there is something new notation, new terminology here. This complex plane, the right half of complex plane, I will write it in terms of magnitude and phase angle. That's it. Okay, so magnitude r and phase angle e raised to j theta, and the phase angle of e raised to j theta is theta. So is it sufficient? No. We should apply limits, saying that limit r tends to infinity. Okay, limit r tends to infinity. So there is a typo here. This should be r into e raised to j theta. So that is path BCD. Then what about path DA? Path DA is something where omega is tending to minus infinity, and again it tends to 0. From minus infinity to 0, you can say. So all paths are covered, 0 to infinity, then 90 to 0 degree, 0 to minus 90 degree, then minus infinity to 0. So these are the points which cover entire right half of S plane. So path AB and D are somewhat similar, they are symmetrical. So there we need to substitute S equal to j omega. And for the path BCD, you should substitute S equal to limit as r tends to infinity, then r into e raised to j theta. Okay, so finally we should substitute these points on the GH plane for GH function, then apply Nyquist theorem or Nyquist criteria. So now we'll take this same example. Now our contour is entire right half of S plane, and let us check mapping from entire right half of S plane to GH plane for GH function. Should we get the same answer or answer will change? Answer will not change because closed loop system is already unstable. Even if you consider the entire right half of S plane, it should give you the same conclusion mathematically. So I'll take this particular example. Draw S plane, locate all the poles and zeros. And one pole will lie on the GH plane, sorry, right half of S plane. Okay, so that pole is nothing but P. The poles of GH that lies in the right half of S plane. So we have one pole of GH that lies on the right half. So P is equal to 1. This should be your first step. Next, what is N? How many encirclements around minus 1 on GH plane need to be found? So let us map entire right half of S plane on the GH plane. So I will take this S plane. I will show you the entire right half of S plane in this way. So this is where S is equal to j omega, and this is where radius r tends to infinity. So S is equal to limit as r tends to infinity r into e raised to j theta. And the third path is S equal to minus j omega. So this is theta. So I'll mark points A, B, C, D. So start mapping. Let us map path AB first. So this is path AB. Let us substitute S equal to j omega in G of S, H of S. So you will get GH of j omega equals to j omega plus 2 divided by j omega plus 1 into j omega minus 1. Okay, so this mapping is quite different. We are not going point by point. Instead, we are going the entire line. So we assume 0 to infinity. Okay, so there is no point by point mapping here, and this is what the actual Nyquist criterion, or this is how the actual numerical should be solved from this point onwards. I mean this numerical onwards. So I'll write the gain as omega square plus 2 square 4 divided by square root of omega square plus 1 into omega square plus 1. Oh, there's a typo, that should be plus. Then we will write the phase angle expression. So what is the phase angle? Tan inverse of omega by 2 for the numerator. Then minus, I'll write minus to write the phase angle for the entire denominator. It is tan inverse omega plus 180 minus tan inverse of omega, because it is omega minus 1 and lies in the second quadrant. So what we get finally is tan inverse of omega by 2. Please hold on, we're about to end up in 5 more minutes. So for path AB, first I will substitute limit omega tends to 0, gh of omega. So what is gain? When omega tends to 0, gain is square root of 4 divided by square root of 1. Okay, because this is 1 into 1 plus 1. Please forgive for this. So it's square root of 4. And phase angle is when omega equal to 0, we have tan inverse of 0 minus 180. Because tan inverse of this cancel. So we have only minus 180 here. Then we have for omega infinity. So when omega is infinity, this term will become 0, the gain will become 0. Then the phase angle is tan inverse of infinity minus 180, that is 90 minus 180. So therefore it is 0 minus 90. Fine. So first path AB has been mapped as A dash and B dash. So let us see how it looks on GH plane. The square root of 4 is 2 at an angle of minus 180. So this is minus 2 at an angle of 180. And finally, let me mark the angles also. So A dash is at minus 2. What about B dash? B dash is 0 magnitude at minus 90 degree. So 0 magnitude at minus 90 degree means it is some shape that will end at a minus 90 degree with 0 magnitude. Okay. So we are skipping point by point mapping. We are directly mapping from 0 to infinity. There is nothing wrong in drawing this appropriate shape. Okay, this is approximate shape. Next path BCD is something like this, where S is equal to limit R tends to infinity, R into e raised to j theta. So I will write S equal to limit R tends to infinity, R into e raised to j theta in GH function. See how it looks. So R into e raised to j theta plus 2 divided by R into e raised to j theta plus 1 into R into e raised to j theta minus 1. Fine. But limit is tending to infinity, which means R is much greater than 1 and R is much greater than 2. So I can ignore this real part without any loss of generalization. So I will approximate this as infinity plus 2, which is infinity only, something like that. So R and R will cancel. Only one R e raised to j theta will remain in the denominator. So 1 by infinity, R tending to infinity, 1 by infinity is 0. So magnitude is 0. What about the phase angle? Phase angle of 1 divided by e raised to j theta is 1 by theta. And if it comes to the numerator, it is minus theta, because it is e raised to minus j theta, it will become. Therefore, minus theta means we have 3 points here, plus 92, 0 to minus 90, where theta is changing. And the corresponding mapping shows it changes from minus 90 to 0 to plus 90 at zero magnitude. So zero magnitude is nothing but the origin. So it is just a dot. Whatever the angle it shows, it is ignorable because magnitude is zero. So there is no any curve or any shape here. It is just a dot. So the entire curve BCD has been mapped into a dot here. That is the conclusion. And the last one, path DA. So path DA is mirror image of path AB. This much write up is sufficient. No need to calculate. Path. Okay, so this is A dash, this is B dash, then B dash, C dash, D dash are the origin here. Then D dash and A dash, the D and A part will get mapped like this. So the final conclusion now. Z equal to P plus N. So P is 1. What is the N value? N is minus 1 because there is a anti-clockwise encircle. So minus 1 plus 1 equal to 0. So which means closed loop system is stable. Stable. Okay. So that's it.